So welcome back, everyone. So let's start our afternoon session. It's now my pleasure to introduce Dr. Roderik Overzier. He's a researcher from the Observatório Nacional in Rio de Janeiro, but now he's about to start, or starting already, as a visiting professor here at the Astronomy Department of University of São Paulo. And he's a researcher mostly in the formation and physics of galaxies in local and high redshift universe. And he's going to talk about his research and perspectives for the giant telescopes.
Thank you. Before we start, I would like to extract some information from the audience. So please raise your hand if your main activity is in instrumentation. Okay, that's about 10 of yours. Please raise your hand if your main research activity is in stars and planetary systems. And last, galaxy evolution and cosmology. Okay, so we have a good mix. I hope my lecture will be accessible to anyone. Please feel free to interrupt me if you want to ask something. So let's see. So I started by writing down my goals for this talk. So assuming that not everybody's going to just wait around until 2024 until we can use GMT, my first goal, my main goal for today is to provide you with some information that is relevant to you today. And of course, we'll try to project into the future what we can do with GMT, what discoveries will be made, things that will be most interesting when GMT comes online. And as Rebecca already mentioned on Monday, this is extremely hard, and she gave the example of the Galactic Center. And I found 4 other examples. So there's a discovery of galaxies at redshift 3, the spectroscopic redshift of gamma ray burst hosts, identification of type 1a supernovae for cosmology at high redshift, and discovery of extrasolar planets. These were all fantastic discoveries with the Keck telescope that didn't make it in the Keck science case written in 1985. And so this is sort of a black box of what's going to happen. Now my second caveat for today that makes me a little bit nervous about predicting science for GMT is the James Webb Space Telescope. So we don't need to wait until 2024 for the next giant telescope. Here you see some recent images from the James Webb Space Telescope that will be launched probably early 2019. So here's some pictures of the mirror assembly folded as it will go into the rocket. Here's the unfolded mirrors, the giant sun shield unfolded that the telescope will sit on, and then probably the 2 main workhorses for James Webb Space Telescope, NIRCam and NIRSPEC. And I hope and I bet that as soon as we turn on these instruments, this will completely revolutionize the field in galaxy evolution. And I hope it will. It means that it was money well spent. And so this makes it particularly hard to predict what exactly will be left to do with GMT. So what is the science that we can access with GMT? So earlier today, Matthew presented how the science drives the technical requirements of the instruments. I turned this around, and so given the parameters of the telescope and the instruments that we have, what is the science that we can do with this? And so the science is a function of your mirror size, your aerial coverage, the wavelength range, spectral resolution, the targeting method, and of course your own interest. And so for the GMAX spectrograph specifically, we're talking about 22-meter telescope, maybe a 17-meter telescope at first light, about an 8 arc-minute rectangular area on the sky, maybe twice that using manifest. Wavelength range between 0.3 and 1 micron at a resolution of a few thousand. And then this instrument will have the space for tens of spectroscopic masks, each with room for hundreds of small slits. Of course, it will be a seeing limited instrument in the optical. And so then I arrive at the following main science areas. The first, I call this all local stuff: interstellar medium, Milky Way archaeology, local group dwarfs, and exoplanet atmospheres, as we saw on Monday. And then the other areas are related to galaxy evolution at high redshift. And I will use 2 popular popular terminology, cosmic noon and cosmic dawn, and I will explain what these are. So what is shown here is the history of star formation in the universe. It's a simple plot. We have redshift or time, going from right to left. And on the vertical axis, we show the total rate of stars being formed on average per unit volume of the universe. I marked here for you the moment when about 10% of all the stars in the universe had been created. This happened at redshift 3, or when the universe was about 2 billion years old. And 50% of all the stars in the universe have been created by about redshift 1. The universe is about 6 billion years old. There's two lines here that have to do with dust corrections, and I will talk about this later. And then here, for the sake of today, I will distinguish between two cosmic epochs that are not very well defined, but I'll describe what they are. So the first is cosmic dawn, and the second is called cosmic noon. So if you see the history of the universe as a day, then early in the morning, you have your first sunrise. In the case of the history of the universe, we're literally talking about the first sunrise. So it's when the first stars and galaxies formed. And this also coincides with the Epoch of Reorganization that I will talk about towards the end of my talk. And this period roughly covers the first billion years of cosmic time. And then the second period, cosmic noon, is sort of as when the main formative epoch of the universe was over. Most galaxies, like the Milky Way, had formed roughly half of their stars. And the star formation, the overall star formation in the universe, entered a period of decline. Okay? We live in the cosmic twilight, yes. So even though the cosmic dawn is insignificant in the total amount of stars that is being produced during this first 1 billion years, it's only a few percent of the total, it is the period that we know the least about, and that makes it, by definition, super interesting. So cosmic dawn is the epoch of the first stars and galaxies. It's a time when we have to search for the seeds of the first massive galaxies and supermassive black holes. And I will also show later on in this talk that already in this time we will find the seeds of massive galaxy clusters in large-scale structure. And it's also the period when the intergalactic medium transitioned from being completely filled with neutral hydrogen, so-called cosmic dark ages, to being completely ionized. And this period is called Epoch of Reorganization. And cosmic noon, so it's the epoch when today's typical galaxies, let's say Milky Way type galaxies and their satellites, were most actively forming. So what do I mean by most actively forming? It's when they acquired most of the mass in stars and black holes, and also started to reach their present-day morphologies. So this is somewhere around redshift 1 to 3 for typical, let's say, Milky Way galaxies. But you can stretch it a little bit if you want to include lower mass galaxies that formed relatively or slightly later, or more massive galaxies than the Milky Way that forms somewhat earlier. Okay, so this is not a very sharp boundary. So in the beginning there was cosmic dawn. Coming out of inflation, we have to wait about 200,000 years before interesting stuff starts to happen, at least from a baryonic perspective. So the Epoch of Recombination is when the free nuclei and electrons first combine to form neutral atoms. This happened at about 240,000 years after the Big Bang. And then we have to wait until another 100,000 years or so later. Photon decoupling and less scattering. So this is when photons, for the last time, interacted with baryons. And now the IGN becomes fully transparent. And so this happens at about 350,000 years, or a redshift of 1100. And it's the epoch from which we have the information from the cosmic microwave background. And then we have to wait probably a few tens of million years until the first stars and galaxies start to form. They produce ionizing radiation. It will ionize the neutral IGM, first in small bubbles surrounding these first sources. And eventually all these regions of ionized hydrogen will overlap, and the intergalactic medium will become fully ionized or reionized. And so depending on cosmology, this period probably started somewhere around redshift 20 to 30, ending somewhere around redshift 6 to 10. Okay. So what's interesting is that it's the cosmology that tells us what's the rate of growth of structure in the universe. And then this will determine the rate of the production of stars that produce ionizing photons. And this is what causes reionization. So in a way, if you study reionization, you're actually following the formation of the first structure in the universe, and vice versa. Okay. There's important observational tracers of this cosmic dawn epoch and reionization. So the earliest time, which are dominated by the neutral hydrogen, are best probed by radio arrays that are sensitive to the redshift of 21 centimeter emission of the neutral hydrogen. So there are lots of radio experiments underway. LOFAR in the Netherlands already operating. Murchison, whatever the W stands for, array in Australia. Thank you. And square kilometer array in the future. And these will be instruments that will be mostly sensitive to the earlier period, maybe late stages when there is still a good mix of ionized and neutral hydrogen in IGM. And then relatively late times can be probed by optical and infrared telescopes, HST, JWST, Subaru, GMT, that can look for the ionizing sources and the state of the IGM. So it will be more and more ionized. And here I've sort of sketched out the timelines of these different instruments as they come online over the next few years. Now then, switching to cosmic noon, I already said that sort of covers the peak of this star formation rate history of the universe. Here on the right I'm showing the same, but then it's the time integral of the star formation rate density, which is the stellar mass density. So it shows you the total amount of stars formed in galaxies at any given redshift. So if you integrate this curve over time, you get the total amount of stars formed. And some of the main questions that relate to this epoch are: what were the physical processes that drive the shape of this star formation rate density and the stellar mass density? How did the Hubble sequence of morphologies come along? And where did the relation between central massive black holes and their host galaxies occur? And ideally, we would like to have all of this as a function of dark matter, halo mass, redshift, etc. Now, what are the main observables of the cosmic noon epoch? Well, most of our current knowledge on, let's say, the stellar ionized, stellar properties, neutral ionized gas, and black holes in galaxies in the relatively local universe is based on rest frame optical diagnostics. So morphologies, kinematics, etc. And so for the redshift range that we're talking about here, cosmic noon, all of this happens in the observed near infrared. Okay, so I wrote down a few sort of key science projects that are perfect for GMTIFs, and that luckily Matthew this morning discussed in quite some detail. And so GMAX doesn't have a lot to offer to this. But as I will show, GMAX is, however, perfectly suited for probing another important ingredient, which is the connection between gas and intergalactic medium that drives the galaxy formation and the galaxies. And it does so by mostly rest frame UV absorption line studies. And so at these redshift range, this happens in the observed optical. So this is perfect for GMAX. So here's a list of sort of the main questions that are, at least on my radar, sort of covering this period from cosmic noon to cosmic dawn. So how do we interpret the cosmic star formation rate history? What's the relation between morphology and kinematics of stars and gas in galaxies? How do the inflows of gas happen? And what is the role of outflows? I'll talk about this later. How do galaxies evolve according to stellar masses and metallicities? What are the seeds of galaxy bulges and black holes? How did they evolve? Which were the first sources that caused the reionization? Were they faint galaxies? Were they quasars, etc.? How did this process happen? What is the role of the environment? Galaxies are not isolated systems. This is important too. And eventually, what's the role of the cosmology in all this? Now, the higher we move in redshift, the younger galaxies become. And this simplifies a lot of these questions. And so in the next 10 or 20 slides or so, I will talk about specifically starburst galaxies that turn out to be the key to understanding, let's say, the basic principles related to all of these important questions. Okay. So let's talk about starbursts. So starburst is a term that is often used quite loosely in astronomy, I find, but you can actually give definitions to this. And I will give you a few definitions, tell you exactly what starburst is and why it's important. So the first definition is related to the theoretically maximum star formation rate that you can imagine that a gas cloud can produce. Okay, so stars are produced from gas, and so the maximum rate that you could possibly get out of a gas cloud is set by the amount of gas you have available, gas mass, divided by the dynamical timescale. Okay, the dynamical timescale is set by a radius divided by a velocity dispersion in the gas. The gas mass can be expressed as a gas fraction of the total amount of the baryonic mass. In this case, I used the dynamical mass. I should create a starburst there. And the dynamical mass can be expressed as proportional to the radius of the system, gas velocity dispersion squared. And so from that follows that the maximum star formation rate that your gas cloud can produce can be written as the gas fraction times gas velocity dispersion to the third power. Okay. So here's an example. So assume that you have a gas fraction of 100% in a very compact galaxy with a radius of 1 kiloparsec and a velocity dispersion of 100 kilometers per second. And the maximum rate of star formation that you can get out of this gas cloud is around 200 solar masses per year. Okay. So here's some examples of star-forming systems. So local galaxies like that are involved in a merger, they can produce starbursts. And the gas fractions in these mergers are not particularly high because these are low redshift, pretty evolved galaxies. But the reason why they're able to crank out a lot of new stars is because during the merger, the gas gets compressed into a very small region. Okay, so it reduces the effective radius, increases the gas fraction in this small region, and the dynamical times will be very short. Okay. Here's an example of a local dwarf galaxy that is not particular in velocity dispersion or radius, but they tend to have a high gas fraction. So dwarf galaxies that have relatively high star formation rates for their masses. Now here's an example of high redshift galaxies, such as Lyman-Alpha galaxies. They sort of have the best of everything. So these are young galaxies, so they're still very compact. Gas is coming in at a high rate, so the gas density is very high. Their gas fractions are very high. Gas velocity dispersions tend to be high as well. And so they win in every parameter. And so these high redshift galaxies that we'll show are almost near the starburst regime. Okay, so you can make another definition, and this is related to the time scale of star formation in galaxies. In galaxy evolution, we use a term called specific star formation rate, which is the star formation rate of a galaxy divided by its current stellar mass. And that gives you an inverse time scale. If you're not familiar with this, you can take the inverse of that, which is known as the mass doubling time. So this is now the units are now in time. And basically what it means is that if a galaxy has a mass doubling time of 100 megayears, for example, it will double in mass every 100 megayears. Okay, so, and it turns out for starbursts, the specific star formation rates, it doesn't matter. But, yeah. It matters if the gas fraction is very high, but you have to read the paper to see what definition one uses. But this assumes that you do not know the gas mass. So that's why the next slide I'll show you a case for the gas. So for starburst galaxies, the specific star formation rate is higher than 10 to the minus 9, 10 to the minus 8, or mass doubling times of around 100 to 1,000 megayears. And you can take the two plots that I showed earlier, the cosmic star formation rate density and the stellar mass density, right? Star formation rate, stellar mass, divide these two curves by each other, and you get the cosmic evolution in the specific star formation rates. Okay, and then you see that as you reach a redshift of 2, 3, and higher, basically all these star-forming galaxies are in the starburst regime. Okay. Now you can also look at the gas. So another way to look at these systems is you have a limited amount of gas available for star formation, you divide this gas mass by the observed star formation rate of a galaxy, and you get another time scale. This time scale will tell you when will this galaxy be done turning all its gas into stars. And so here's an example. Assume you have a galaxy with a gas mass of 10 to the 10 solar masses, forming stars at a rate of 100 solar masses per year. Then the gas would be depleted in about 100 megayears. And in principle, the star formation would end. Now, what I've shown here is a plot with measurements of high redshift galaxies. It's not very important what's on the axis here, but basically, the points in this blue line here tell you what's the typical age of these star-forming galaxies. And so a lot of these high redshift galaxies, they have ages of more than 100 megayears, up to 1 billion years. And so even though we call these galaxies starburst galaxies, they are not bursty. Okay, so the starburst is not a one-time event. Basically, these high redshift galaxies are continuously forming stars at a high rate. Okay, and they do so. High Z galaxies are not bursty. And what this means is that as these galaxies burn through their gas, there is continuously new gas being added to the system. Right? Otherwise, these starbursts, they would stop after about 100 megayears or so. And the fourth definition I wanted to share with you is related to star formation rate intensity, which is defined as the star formation rate of a galaxy divided by its surface area, or if you know it, its volume. What is shown here on the right is the very well-known relation known as the Kennigan-Smit Law, and that tells us that there is a linear relation in this log-log plot between the star formation rate density, so solar mass per year per square kiloparsec, and the gas surface mass density. So down here we have galaxies like the Milky Way, and starburst galaxies are here on the top that have star formation rate densities many orders of magnitude higher, but they follow the same relation. So here's an example. Assume you have a starburst galaxy with a radius of 1 kiloparsec, forming stars at a rate of 100 solar masses per year. And the star formation rate per area will be about 30 solar masses per year created per square kiloparsec. And do the same calculation for the Milky Way. Take a radius of about 10 kiloparsec and a star formation rate of 1 solar mass per year. And now we get 3 times 10 to the minus 3 solar mass per year per square kiloparsec. So in starbursts, the star formation rate intensity, right, star formation rate per unit area in your galaxy, is up to 10,000 times higher than that of the, let's say, any region in the ISM. And it's going to have quite drastic consequences for your galaxy. So here are these 4 definitions. So we have the theoretical maximum possible star formation rate, star formation time scale, gas depletion time scale, and the star formation rate and density. Now you can find many regions, even inside the Milky Way, nearby galaxies, that qualify as starbursts. So I show here the example of the trapezium cluster in the Orion Nebula, or 30 Doradus, which is a big star-forming region in the Large Magellanic Cloud. So these regions qualify as starbursts if you go through these calculations. But starburst galaxies are unique because they satisfy these criteria as a whole. Okay, so here's an example of M82, which is a starburst galaxy. Milky Way has starburst, but it's not a starburst galaxy. So let's say you are a starburst galaxy. How is that going to affect your life? Well, first of all, the high star formation activity requires that you have the gas to drive the star formation. And this usually means that you need some inflow mechanism to drive the gas from intergalactic medium or other galaxies to your galaxy. And so inflows means you need a delivery mechanism. This could be bars or bars in bars, as Thaisa talked about. Mergers, other types of accretion events. So here's some examples of circumnuclear starbursts that are probably driven by gas inflow in bars. Merging galaxies. In the case of the Milky Way, there's a small fraction of the star formation that can be explained by gas that is delivered to the Milky Way through the infall from nearby satellites. Now, in starburst galaxies, we actually observe that their star formation rates are very close to this theoretical maximum star formation rate that I talked about. And this means that the inflows need to be rapid, and they need to be always happening. And so what's shown here is a data point. So this is showing galaxies at redshift 2 with star formation rates observed of around 100 to 200 solar masses per year. And then this blue line here gives you a prediction for the number of dark matter halos that may have gas accretion rates high enough to sustain such high levels of star formation rate. Oops. And so the observation is pretty close to this curve, meaning that these galaxies are halos that have a certain mass accretion rate, almost always harbor a galaxy that is forming stars at a high rate. And then this has given rise to different accretion regimes called accretion, a mix of cold and hot gas and sort of intermediate mass, intermediate redshift halos. And then in the more nearby universe where the cooling times of the gas that is in principle available for star formation are just too long. And so not a lot of gas makes it to the center of these halos. And such systems will not be associated with a lot of star formation. At high redshift that we're concerned about, we're mostly in one of these two cold accretion regimes. Now, I mentioned that starbursts have a high star formation rate intensity. And according to this relation between the surface density of star formation and gas, this means that a galaxy with a high star formation rate intensity will also have a high gas column density. Now, dust is mixed in with the gas, so if you have a high column density in gas, then you also will have a higher extinction. We can see that if we plot in a set of nearby galaxies the observed star formation rate versus the mass in dense molecular clouds, there's again a very good correlation. Okay? And this comes from the fact that the gas density is strongly correlated with the star formation rate density. Now, in principle, this could be a big problem, especially at high redshift. So, if high star formation rate densities lead to high gas column densities, and this will lead to high extinction, then this can give you practical observational problems, especially if you're observing in the red frame UV, which is what we're doing at high redshift. So here's an example of a local galaxy that has a high star formation rate, sort of equivalent to typical galaxies at high redshift. These are HST images, far UV, near UV, and most of the light is just extinguished by the high column densities of gas and dust. And then you go to I-band, and you see the two galaxies there. Now, in principle, we have pretty good techniques to use the color in the UV to correct for dust obscuration. But if you're missing most of the UV light to begin with, then even this correction will be hopeless. Okay. Now, luckily, there's good news at high redshift. And so, of course, the dust that we have in typical local galaxies that gets compressed when galaxies, especially when galaxies merge, a lot of this dust wasn't around yet at high redshift. Okay? Dust needs to be produced, first by supernovae, later by evolved stars. So the higher you go in redshift, the younger your galaxies will be. You'll have lower metallicities, lower dust masses, etc. And so what is shown here is sort of it's the typical amount of light extincted by dust in galaxies between redshift 3 and 6, and then for 3 different bins of star formation rate. And so there's 2 interesting observations here. For galaxies, let's say, in each bin, the amount of light extinct by dust decreases with increasing redshift. And this is probably because a lot of this dust wasn't around yet at the highest redshifts. So it takes some time to build this up. And the second interesting observation is that as you go to galaxies with relatively low star formation rates, the dust is always low, right? And it has to do again with that a lower star formation rate will have a lower associated gas column density. Now you can combine all these effects, and you can calculate what is the fraction of, let's say, the star formation rate density that comes out in the UV at each redshift compared to the infrared. So that result is shown here. So everything that's in blue is, let's say, star formation that you will have no trouble detecting if you observe in the red frame UV, observed optical at high redshift. And red is the amount of the star formation, or the amount of light that is lost in the infrared. As you go higher in redshift, the UV gives us nearly a complete picture of the entire star formation rate density. By the time we get to redshift 7, maybe 10% of the star formation rate density, or total ionizing luminosity, is lost to the infrared. The lower redshift limits here, this is actually important. And so when you see these plots of the cosmic star formation rate density evolution, there's always two curves given. So the blue is what's observed, and the orange is the correction after correcting for dust. And so what you see is that when, at least as the cosmic dawn is concerned, these curves are very close together. It basically means that the dust is insignificant at high redshift. This is good news. So let's go on. So I mentioned to you that starburst galaxies have a very high star formation rate per unit area. And so that means that you have a very high energy density or radiation pressure on your ISM. You also have a very high supernova rate per unit volume or per unit area. And this will give you winds, or very strong winds. These winds will mix the gas, and if the winds are strong, if the winds have velocities that are higher than the escape velocity of the potential the galaxy sits in, the wind will lead to an outflow, okay, which returns the gas to the intergalactic medium. You can estimate what is sort of the maximum wind speed that you can get out of a starburst, and so this has all been set in typical values, and sort of the maximum velocity that you can get out of a starburst is about 2,000 kilometers per second, okay, which is larger than most escape velocities, typical galaxies. We see these winds in the form of hot X-ray emitting gas, in the case of M82, a nearby galaxy, where we can use X-ray observations to probe these outflows. At high redshift, we cannot use X-rays; we just don't have the sensitivities and resolutions. But there are other tracers of these winds. One of the most popular tracers is this magnesium-2 doublet, which is a feature at 2800 angstroms rest frame. And what you're seeing here is the magnesium-2 emission and absorption in a starburst galaxy, some high redshift. The green line here indicates the systemic velocity of the galaxy, and then you have this blue absorption component that is blue shifted. And so this is related to the ionized gas that is coming towards us, has been launched in the wind, and is absorbing the light at these wavelengths. And so you hear this is done in a velocity scale, so you see that the maximum amount of blue shifted absorbing gas has a velocity of about -1,000. Okay, so it's pretty close to this maximum wind speed. So this is a way to go and study these winds in high redshift galaxies. Now, if you're forming stars at a high rate, you're also rapidly building up dense stellar structures, star clusters, and some degree of seed black holes, probably. Now, this is important for even old and evolved galaxies. So if you look at the surface brightness profiles of early type galaxies in the nearby universe, these are very old evolved galaxies. They basically fall apart in two different types. There's very massive ones, and there's sort of typical lower mass ones. And especially these objects, they have what's called a cusp in their nucleus. So there's an excess of light relative to what you would expect for a simple divocular profile. And this nuclear cusp is believed to be related to the starburst at much earlier time. So at high redshift, we see compact and old galaxies, which are probably the progenitors of these nuclear regions of typical early type galaxies today. And we also have examples of objects in which these compact nuclei are first forming. So what you're seeing here is a very massive starburst. It's only a few mega years old, that has the right mass, size, and stellar mass density to be the progenitor of these nuclear cusps in early type galaxies. Now, if you're forming dense stellar structures and there's a black hole present, let's say a seed black hole, couple this with the gaseous inflows that are happening anyway in these starburst systems, and this will lead to AGN fueling and black hole growth, as Thaisa explained in detail in her lecture. This plot here, maybe it's a little bit confusing, but it's showing again the cosmic star formation rate density. And here people have made an attempt to also estimate the accretion rate of all black holes on average. So this is done using, I think, the X-ray background. So we can measure this out to redshift 1 or 2 or so. And the black hole mass accretion rate has a very similar shape to the star formation rate density. Here on the right, I'm showing a known correlation between the mass of black holes in nearby galaxies versus the number of globular clusters that these galaxies have. And there is it's not a tight correlation, there is a correlation. Okay, and the idea is that the growth of the black hole is related to the same inflows that are responsible for starbursts, and some fraction of these starbursts will lead to, let's say, dense stellar systems like globular clusters, then you expect that these observables track each other. And so this is sort of evidence that the same mechanisms that drove star formation also are related to the ones that grew the black holes. So black holes and inflows lead to AGN fueling and black hole growth, but I have told you that the outflows in these systems are very strong. Okay, so the only way you can get inflows into the nuclear region of galaxies to grow black holes means that the outflows must be weak. What is shown here is a relation between star formation rate in galaxies and their hard X-ray luminosity. This relation comes about mainly due to the population of high-mass X-ray binaries, right, that produce hard X-ray radiation. So if you have a higher star formation rate, you have more of these systems, and so there's a correlation between the two. Now, if you have in addition a growing black hole in these galaxies, you would expect an elevation in the hard X-ray signal. If you plot typical high redshift galaxies for which we have tried to measure this at high redshift, they basically don't deviate very much from this relation. And in fact, this blue line indicates the limiting sensitivity that we currently have in the deepest X-ray observation. You stack all high redshift optics together, and this is sort of the upper limit on the hard X-ray luminosity that you get. And so we know that the fraction of actively growing black holes in high redshift starburst galaxies is actually very low. It's of order 1 to 3%. And it may be because these galaxies are still in their outflow dominated phase. We have to wait for the outflows to settle down, and then you can have the type of nuclear inflows that you need to further grow the black hole. Now, the role of environment is important as well. What is shown here is the halo mass of objects at redshift 0, redshift, and then color-coded here is when these halos, or the progenitors of these halos, experience their highest star formation rates. So if you look at, let's say, a galaxy cluster today, so we're talking about a halo mass between 10 to the 14 and 10 to the 15 solar masses, the galaxies that make up this halo today reach their peak star formation rates somewhere around redshift 3 or 4. Okay? If you go to, let's say, a typical Milky Way type galaxy that lives in a halo of a few times 10 to the 12 solar masses, it reached its peak star formation rate somewhere between redshift 1 and 2. Okay? So the star formation rate density for massive halos is a little bit peaks earlier than for lower mass halos. Okay, so this is important to keep in mind. Now, all of these principles that I've shown you are relevant to starburst galaxies at any redshift: local starbursts, local infrared luminous merging galaxies, high redshift Lyman-break galaxies, Lyman-Alpha emitters close to the Epoch of Reorganization. It's just the relative importance of all these different processes. It's going to depend on the mass and the redshift, etc. What am I doing with time? So let's go back to GMAX now. I'll give you some applications with GMAX at cosmic noon and then at cosmic dawn. So as I mentioned, a lot of the, let's say, typical galaxy evolution stuff in cosmic noon occurs in the observed near infrared. So it's really the domain of GM tips. I think the unique angle we can attack with an instrument like GMAX is the connection between gas and galaxies. So here you see a simulation, distribution of gas, distribution of the stars. And whatever the gas is doing, this is a completely unprobed parameter space right now. Here you see a cosmological simulation showing the inflow of gas in a dark matter halo. And this is actually 5 different simulations of the same system that include different recipes for supernova feedback, AGN fueling, cooling, etc. And depending on how you set up your simulation and what choices you make, you get actually a very different distribution in gas and galaxies. Okay. And so the only way, I think, to make progress in this is to actually get observational constraints. This has been done on a limited scale in the past few years. And the ways it's been done is by pairing up high redshift galaxies with quasars that are behind these galaxies. So you look for projected pairs, distant quasars. A galaxy is a little bit closer. And you take a spectrum of the quasar, and whatever gas sits around the galaxy will cause an absorption feature in the spectrum of the quasar. So that has been done for many pairs of Lyman-Alpha galaxies, in this case around redshift 2. And this is showing the stacked spectrum in the rest frame of the Starburst Galaxies at different impact parameters. And so you see, you can focus here on the carbon-4 and Lyman-Alpha absorption. So there's an absorption feature there that you can trace just about 100 kiloparsec away from the galaxies. Okay, so this is giving the first information on the column densities of gas, the metallicity of the gas, maybe the kinematics of the gas, as a function of impact parameter from the galaxy. The reason why this has not progressed beyond sort of this level of detail is because there's not a lot of pairs of quasars and galaxies. Okay? And so the big advantage comes when we have spectrographs and telescopes that are sensitive enough to not use background quasars but use background galaxies. Galaxies are much more numerous than quasars. So if you have a spectrograph, you can take lots of spectra of background galaxies. This light will pass through the whole intergalactic medium and whatever is there along the line of sight. And this is showing you here, as the light of these background galaxies passes through the cosmic web, you will get these absorption or let's say enhancements in the optical depth of the gas at specific redshifts where there is structure. You can even measure then an overdensity of gas, velocities and temperature of whatever is between you and these background galaxies. Here's a simulation that shows this quite nicely by Mukai et al. 2017. So the symbols here show the distribution of galaxies at redshift, I believe this is redshift 2, in an area of about area of about 100 by 100 megaparsecs. And then in color here is the net total absorption expected along the line of sight. Okay, and so you see that wherever you have a lot of galaxies clustered together, you'll find this delta F, which is the net gas absorption signal, is more negative. So it means that where the galaxy densities are higher, there'll be a higher gas density. So your absorption signal will be stronger. Okay, so if you can measure this gas, it's equivalent to sort of measuring the distribution of galaxies and structure, and that then allows you to explore the connection between gas and galaxy formation. Here indicates sort of the field of view that GMAX with manifest will probe, and so this is sort of a good match to some of these voids and overdense regions that you expect. Here's an example of a simulated massive galaxy cluster when it's still forming at redshift 2.5. So these are the largest type of structures that you can expect in the cosmic web. So this is the dark matter density distribution of a massive galaxy cluster as it is forming at redshift 2.5, and this is sort of the predicted gas absorption distribution. Okay, and so if I indicate again the GMAX field of view, this is a perfect match. So if you're like me and you're interested in the formation of galaxy clusters, then this is a perfect instrument. Of course, these systems are very rare, right? So they are. If you look at this larger field again, it's just these very dense rare regions, so you would have to map a large region to find a few of them. Now, the accuracy with which you can map the gas density in the cosmic web is going to depend on the number of background sources of which you can take spectra. Okay, so the more sources you have in the higher density of sources in your background, the more spectra you get along the line of sight. And so the impact parameters, or the resolution with which you can reconstruct the distribution of gas in the cosmic web, will increase. And this is showing a simulation from paper Lee et al. This is a simulation for an 8-meter telescope. So as the exposure time goes up, the number of background sources that are becoming that you will be able to observe at high enough signal to noise will go up as well. And so if you have a higher density of sources, you can reconstruct the cosmic web at a higher spatial resolution. So if you do a 20-hour observation, you have about 3,000 background galaxies per square degree, and you can reconstruct the gas distribution in the cosmic web at a resolution of about 1 megaparsecs. Now, why does GMT help with this? It's just the speed of obtaining these spectra. So here you see a simulation of an observation of a redshift 5 galaxy, so let's say a background galaxy, magnitude 25, observed at 2 hours using KEC-DMOS, and then the same object simulated for 2 hours with GMT GMAX. Okay? So you can either so you use the same amount of exposure time, you get a much higher signal noise spectra. You'll be able to detect these absorption features along the line of sight in much greater numbers, or you can decide that this is sufficient signal to noise, so you could probably acquire these spectra in 10 minutes with GMAX. But you can map the cosmic web much faster. Okay, so you can much quicker do a large survey of this kind of cosmic web tomography. All right. So now let's look at a few specific cases of cosmic dawn. So I told you about the Epoch of Reorganization. So it's the period when the intergalactic medium transitioned from being completely neutral to completely ionized. The speed and the moment at which this happened depends on the rate of the production of ionizing photons, right? And so there's two main ingredients that go into this calculation, or let's say exploration of this Epoch of Reorganization. The first thing you need to know is the total rate of ionizing photons that is being produced by all the galaxies at any given time as a function of redshift. So we think we have this under control pretty well now using HST. So what you see here are the luminosity functions measured in the Restrein UV, redshift 4, 5, 6, 7, 8, 10. And so if you integrate along these curves, this will tell you what's the total amount of photons being produced in the UV, and from that you can, if you assume that you know the initial mass function, stellar population, you can calculate the total rate of ionizing photons. So these are the photons that have an energy higher than 13.6 electron volts, which is what you need to ionize the neutral hydrogen. Now the second ingredient here is more complicated. This is the escape fraction, and this is related to the amount of these ionizing photons that are being produced in starburst galaxies that actually makes it out of these galaxies into the intergalactic medium. And this is actually a problem. We do not understand at all how this process happens. And the reason for this is because typical star-forming galaxies have neutral hydrogen column densities that are 4 to 10 orders of magnitude higher than those that you need to absorb all the Lyman continuum photons that such a galaxy produces. And normally star-forming galaxies are always surrounded by these large column densities of gas, which is actually what allows them to have these high star formation rates to begin with. Okay? And so there's little to no evidence, not theoretically, not observationally, that any of these Lyman continuum photons that we need for the reionization to escape these high redshift galaxies. So what you see here is two different observations. The first is a sample of galaxies of redshift 1 observed with HST using a filter that is just above the Lyman continuum break, and one that is just below it. And so even though these galaxies are producing a lot of ionizing photons, none of them has come out below the Lyman edge. Okay? So all of these photons will be absorbed. In the redshift 3, we know a few examples. So these are images, these are spectra. There's 2 galaxies. This is where the Lyman limit is, and there's a few cases where we see a little bit of light leaking out of these galaxies. So these are the photons that you need in order to produce the reionization. It's a small fraction of photons that's coming out per galaxy, and it's a small fraction of all galaxies in which we see this. Okay, so this is a big problem. Now, 2 years ago, we had a small breakthrough, and that's because we found a galaxy, and it was the first case where we found a significant amount of Lyman continuum photons coming out. And this was a nearby galaxy, so this means that not only did we find evidence of a galaxy in which this process is happening at an impressive rate, we could also try to understand why this is happening in this galaxy. And so there are 2 important clues. What is shown here is a rest frame UV spectrum from HST, showing the silicon-3 absorption line, which is like the magnesium-2 doublet that I showed you earlier. It's a line that probes the ionized gas in these Starburst galaxies. I've indicated again the systematic redshift of the object, or velocity, by this vertical dashed line. And so this absorption feature is shifted towards the blue by 1,000, 2,000 kilometers per second. And so it means that the galaxy that is leaking these Lyman continuum photons has an interstellar medium that is experiencing a very large, a strong wind or outflow. Now, if you look at the Lyman-Alpha emission in these galaxies, typically this Lyman-Alpha line, which is a resonantly scattered line, you only see emission on the red side, which are the photons that have energies too low to resonantly scatter, and so they make it out of these starburst regions. But you never see emission on the blue side, because these Lyman-Alpha photons, they scatter of neutral hydrogen that sits around these galaxies, and so eventually they'll hit a dust particle, and they're absorbed. However, in this case, we see very strong blue-shifted Lyman-Alpha in emission. So what it means is that the high supernova rates in this compact starburst has punctured a hole into the interstellar medium, so it has removed all the neutral hydrogen along the line of sight. The Lyman continuum photons can escape through this hole, and then the Lyman-Alpha photons that are part of this wind, they will also not experience any neutral hydrogen. So that's why you see the blue-shifted Lyman-Alpha photons that are sort of riding this wind. Okay, and so Gmax will be perfect to look for these kind of signatures in the rest frame far UV in spectra up to redshift 7. So it's interesting. It will be interesting to see if this is sort of the process that we need in order to understand the reionization. Now, there are some other indicators that we use to try to study this process of reionization. I talked about Lyman continuum escape. Another one is the Lyman escape fraction. And I'll explain this in this slide. So, as I said, Lyman-Alpha photons are produced in starbursts, and they typically resonantly scatter off neutral hydrogen atoms until they reach the dust particle, and they're gone. Okay. Now, as the intergalactic medium becomes more and more neutral as we go further towards cosmic dawn, we may expect a sharp drop in the fraction of galaxies that is bright in Lyman-Alpha, okay, because of this process. And so the Lyman-Alpha, the fraction of galaxies that have a strong Lyman-Alpha line, also indirectly probes the reionization. So you may expect that as you go to higher and higher galaxies, this Lyman-Alpha has a harder and harder time to get out of these galaxies because they're more and more surrounded by neutral hydrogen. And so the fraction of galaxies that is bright in Lyman-Alpha should go down, exactly as this observation shows you. However, this observation has been widely disputed, and is based on a very small number of galaxies. I can show you other panels from the same paper that show that this effect doesn't exist if you make slightly different sample selections. And so to do this really well, let's say you want to target a few hundreds of these kind of galaxies close to redshift 6 or 7, you can do this using 20 Gmax masks, observing these galaxies about 2 hours per mask. So this is a very reasonable project that could solve or could settle this question. Now it gets really interesting when we can combine observations of galaxies with what the gas is doing. Okay, so the Epoch of Reorganization is all about transition from an IGM that is dominated by neutral hydrogen emission to an ionized medium dominated by light from the galaxies. What is shown here is a simulation, redshift 6.6, somewhere towards the end of reionization. It's showing the temperature of the gas, so the brightest temperature of the H1 gas that radio surveys could in principle detect, and the distribution of Lyman-Alpha emitting galaxies. And what you see here is that there where the gas densities are high, you have a deficit of Lyman-Alpha emitting galaxies. Right? So in other words, these regions here, they haven't been reionized yet. Okay, so I have to wait a little bit longer before galaxies to form in these regions and ionize all the neutral hydrogen around them. Okay. So once we have radio surveys that can measure the distribution and brightness temperature of the neutral hydrogen as a function of redshift during the Epoch of Reorganization, we'll be able to cross-correlate the gas densities or gas brightness temperatures, which is what you measure, with the distributions and the properties of the galaxies that we see at the same redshift. And this is a bit of a complicated plot. I apologize for that. It's showing the power in the cross-correlation between galaxies and H1 gas as a function of inverse scale, but I wrote down here, so this is 10 megaparsec, 1 megaparsec, 100 kiloparsec. And then the dotted lines here indicate an anti-correlation. Okay? So what it tells you that on large scales, there's an anti-correlation between the galaxies and neutral hydrogen, which is exactly what you see here, right? On these large scales, you have large regions of neutral hydrogen that haven't been reionized yet, and there won't be any galaxies there. Okay, so you expect an anti-correlation. And on small scales, of course, because the galaxies form from turns neutral hydrogen into stars, you expect a very strong correlation. And the scale at which these cross spectra turn from a negative correlation to a positive correlation sort of gives you the typical size of the ionized bubbles around the first galaxies. So SKA, prime focus spectrograph, GMT will be extremely suitable for trying to do these kind of correlations between neutral hydrogen and ionizing galaxies. I'll skip this slide. And then we're almost at the end. So of course, GMT is not a good telescope to do a large survey and find your interesting targets. And so the targets, especially for Gmax, which is it's a slit or fiber spectrograph, the targets need to be provided from other surveys or instruments. And it's not so easy today to find deep enough surveys, that are deep enough to find, let's say, high redshift galaxies in large numbers over the sort of sky areas that we're talking about for Gmax-sized spectroscopic masks. So there are some existing deep wide surveys that have been done with HST. This is the focal plane of JWST instrumentation. So NearCam and NearSpec will have roughly the same area as Gmax. So that's one way to get your targets. Ideally, you have a larger survey of high redshift galaxies, and then this will allow you to pick the most interesting regions and then design your masks. This allows me to advertise two other projects that we're involved in. First, a Hyper Supreme Cam survey, which is a large galaxy evolution survey in the Subaru telescope that my group in Rio is involved in. And it's sort of a precursor survey for another project, which is another great FAPESP-funded project led by Laertje Sodré. Where are you, Laertje? Laertje? There, but you can also see him there. And so this fantastic spectrograph will have a very wide field of view, and it's on an 8-meter telescope, so you can do surveys that are wide and deep enough, to probe all the way to redshift 8. And I think specifically for Brazil, the combination PFS and then GMT to follow up the interesting sources that we'll find as part of these spectroscopic surveys will be a very powerful combination. And that's the end of my presentation. Thank you very much.
one because that's the first time I see LSST in this presentation. I was all the time thinking about why not LSST? Because the PFS is northern hemisphere, GMT will be south. So the intersection will be not 100%, but with LSST will be.
No, thanks for reminding me what I should have said about this slide. So absolutely, LSST will be, providing very wide areas, deep enough to provide you with targets, at redshift, at least out to redshifts of 6 or 7 or so, that you can then follow up with GMT. Absolutely right.
Roderik, what's the typical or the only resolution of PFS? And for the scientific cases you showed, what's the typical resolution for the analysis you are expecting from GMAX? Because what Rafael will talk about, Claudia and Rafael will talk tomorrow, is that the resolution has a huge impact on field of view and spectral coverage. So we need to select properly our VPH grading.
Yeah, so I'm expecting and hoping, I was expecting that PFS and GMAX spectral resolution will be quite similar. It's of order 4,000 or 5,000 or so. If that's not the case, I'd be interested to hear. Right. Yes, absolutely, absolutely.
So you mentioned several science cases where GMT will make the same thing we are doing, but faster. So it was not clear for me what we will be able to do that we are not yet able to do right now.
Okay, so right now these kind of tomographic studies. Let's see if I can quickly go back. So right now we have had a few studies that have been able to apply this tomographic mapping on relatively small fields. So it's requiring a lot of time on 8-meter telescopes, and the maximum size that has been reached is maybe 1 square degree or so. And so the fact that you can get your spectra faster either means you can map a larger region, for the same amount of time, or you could focus on a narrow region but just go much deeper. So you take higher signal-to-noise spectra of the background galaxies that are there, and you'll get many more absorption systems along the sides that you otherwise would not detect if your spectra are lower signal-to-noise. So you can either increase your spatial resolution, or you can increase your resolution along the line of sight, or you can widen your area to look for, let's say, rare or interesting objects.
Questions?
I don't know if GMT will have director time, things like that, that would allow, for example, a Hubble deep field, a GMT deep field. What could one expect from a GMT deep field regarding, for example, reorganization, things like that?
Can I?
As I said, you need the spectroscopic targets. You need to know where your targets are for GMAX, right? So, it's difficult for me to answer this. So provided we have, let's say, a deep enough target field from JWST, then you could get, if you spend enough time, you'll get the redshifts, outflow rates, Lyman-Alpha fractions of say a few hundred galaxies just around redshift 6 or 7, and you'll probably blow away the competition right there. But I'm hesitating a little bit because I would like to see what happens with JWST soon. This may not be the smartest thing to do.
So the other aspect of this question, we discussed it on the SAC, the Science Advisory Committee. So how would the partners have access to telescope time? So there are two extremes. One is each partner have their own telescope time and their own tax, and they allocate their time, they give their time. If one person wants to observe all the whole time and the partner is okay with that, they can do that. The opposite of that will be for GMT to have a single TAC that all the proposals will be sent there and then approved by the best science. Since we have partners that want one thing and the other, the advantage and the disadvantage in both cases, so far we came up with a mixed system, which is very complicated, but there will be both structures in principle. There's a long time to think about that, but we are going to have both structures working in parallel. A single wide GMT TAC that you can send your proposal there, or if the partner wants, their individual ones. So GMT or Gmax deep field or something like that, it's the kind of science I think it's suited for this overall GMT tech. So it's one thing. So one of the reasons we have this partner by partner tax is that some of the partners, including us, made question of having. So we might discuss this subject for the future. So if it's better to have our own tech or a global tech. I know Australia have a different view on that.
Yes, so let me offer my view on that one. I think that because we've got many partners and GMT time will be divided up into relatively small blocks per partner, that those partners who voluntarily join the common TAC will be able to participate in bigger and more ambitious projects and will rapidly outcompete those partners who do not. Now, I think that the mixed TAC process allows partners to contribute some of their time to a common TAC and keep some for themselves if they want to be conservative. But my prediction is that those partners who join the common TAC will find themselves doing much higher impact, larger and more ambitious programs than those who do the small stuff. And I would strongly recommend that Brazil think hard about not being part of that common TAC, because I think that would be self-limiting.
Thank you.
So that's interesting because currently Brazil has, we're a partner of Gemini. We have chosen not to participate in, for example, the international large program opportunity, which I would be all for it. But.
More questions on high redshift galaxies, connection with the gas?
Roderik, I have a question. Maybe this has already been answered before, but I was wondering in terms of target opportunity. For James Webb, one of the very first targets that they will be observing is going to be the frontiers field. These massive galaxy clusters, they want to really confirm the high redshift candidates to improve the mass modeling. And certainly, first thing would be to observe deep in the middle infrared, and then the candidates will be follow-up spectroscopically with the near infrared spectroscopic spectrograph on board of James Webb. I was wondering if there is any competition for GMT in that sense. Can we do better, faster than James Webb, spectroscopically following up those candidates?
Yeah, although there is a probably JWST probably wins in let's say redshift range you can reach, but I think GMT wins in spectral resolution, it wins in spatial resolution, it wins in sensitivity. Yes, but of course, we have those JWST results in 1 year, right? So I have to see what's there left to be done, 2024.